Usually before I start recording, I get out all my angst and all my swear words, and then I start recording. So Charlotte got an earful, right, Charlotte?
Yep.
Actually, we don't know if Charlotte got an earful because she had trouble hearing me earlier today. All right, so for the nail lab, we were talking about the discussion, and you should definitely start off with, we found the zinc on the nail to be blank millimeters thick. And then you talk about whether or not this seems reasonable. You can't do a percent error on it because you don't know how thick it is. When you comment on whether or not it seems reasonable, you would, comment on what you saw in the video of the nail that has no zinc on it versus the nail that does have zinc on it. And the ruler's laid next to it. You can actually kind of guess how thick it is. And when I say guess, I'm not talking about 0.213 millimeters. I'm talking about, well, geez, it can't be 1 millimeter thick of zinc because that would be the whole nail, right? And it might be 1/10 of a millimeter thick. That could possibly be the answer, because then it would be, 10% of the thickness of the nail. Or it might be a little less than 1/10 of a millimeter. You could, comment on that based on just making assumptions. Like if the nail is, again, 2 millimeters diameter on the shank, and it's 1 millimeter of zinc on both sides, that's the whole nail. Does that make sense?
Yeah.
Okay, so it can't be 1 millimeter. And it seemed to be just a small little smidge of the side of the nail. So you might even guess less than 1/10 of a millimeter. Okay, and then you would also comment on those reactions that she also performs. So we talked about, there's the redox with the hydrogen gas being formed, the pure element from HCl, and zinc, a pure element turning into zinc chloride. There's the gas forming reaction with the sodium carbonate and the HCl, and there's the precipitation reaction where you form zinc carbonate. So you would want to comment on those things too, and that would kind of be your discussion. The assignment kind of helps you with the discussion. Okay, so that was that on. That's what we were talking about with the zinc lab. Have you decided which lab you're going to write up, Issa? Oh, she's on mute.
I thought we were supposed to do it on the, what else?
Carbonate lab.
Yeah, the carbonate lab.
You actually have a choice, the carbonate lab or the nail lab.
Oh.
It was in the announcement that I made.
What? How did I miss that? Like, I read your announcement. I just, for some reason, I guess it was just stuck in my head that I had to do it on that one.
Okay.
Well, and I was going to give you my number so that you can confirm.
What was your number? I can tell you right now.
Yeah, that's exactly what I'm looking for. I'm like, it's, I'm looking at through the box. Is it, no, it wasn't precipitation reactions.
It was probably just some carbonate lab.
It said carbonate? Okay. Huh. What do I do with it? Is it gravimetric analysis?
Yeah, that's it.
So I was number 36.
Yeah.
And before you tell me, let me tell you what I thought it was. Let me look at where's my lab book? Sorry, y'all. I wasn't gonna look for my lab notebook.
Right. Charlotte's patient.
I'm sorry. Y'all can talk about something else. I'm looking through. I don't know why I have so many notebooks. And I'm like, why? They all look the same.
And you said it was 36, right?
Yeah, 36. And okay, I found my lab notebook. And where is it? Spectrometry, no. I'm looking at my table of contents. What is it? What was it titled? Titration?
I put it a formula of a compound by
page 65.
By precipitation or
page
something.
Page 65. It says page 65. Okay, let's see. And the molar mass I found for my carbonate was 130 grams per mole. Doing this experiment, I had an issue during my first attempt, blah, blah. What I had left in my calcium, this may have impacted Mike's as perhaps, blah, blah. Where did I write what it was? I wrote it here, my estimate.
Should be in your discussion.
Normally, we would identify the unformed and blah, blah, must be handled. I found it to be negative 6%. This might be precipitate during the washing. Calcium may not have been. What the heck? Where did I write? The carbonate is likely potassium carbonate, as this carbonate has a mass of 138.205 grams per mole, which is closest to my experimental molar mass.
Okay. So you want to know what you got?
Yeah.
Okay. Number 36 was, oh no, potassium carbonate.
Oh, yes. Awesome.
Did I fake you out at all by saying, oh no?
No, it kind of seemed like you're making it a little too dramatic. So I was like,
Okay. Good. Then I didn't scare you too much.
Wow. So I was off by like, I actually got 130 grams per mole.
So let's talk about your discussion.
But it's two significant digits, so I couldn't.
Right. So, but with your discussion, you would talk about the error based on those types of ideas, that your molar mass was only 2 zig figs. But also you want to explain, was your error negative or positive?
Negative.
Okay, I want to show you something real quick, and I'm going to do a share here. I feel like this is one of those like meetings where you have to share your feelings or something. So I'm going to share with you. So when you calculate the molar mass is equal to the mass in grams over the moles, or the amount in moles, right? And your number was too low. How do I know it was too low when you say you have a negative percent error?
Because it's negative.
Because it's negative. That's why I like negatives in the percent error. Most people don't. But your number was too low. Okay, if your number was too low, what are the two ways to get it? Well, if your mass was too low and your amount was just right, what would that do to your molar mass? If your mass is too low and your amount was just right. So let's say that you said that the molar mass of potassium carbonate is 138. Is that right?
Yeah. Mm-hmm.
Okay. So let's say that you got 1 mole here, so it's just right, and you got 132 grams for your mass. So what does it mean if your mass was too low? It means that you don't know how to use a scale, right?
Okay.
So
I may have also lost.
Well, we're just doing these one by one. So if your mass is too low, that would give you a molar mass that's too low, right?
Yeah.
And that means you can't use the scale. Now, what else would give us a molar mass that is too low? So let's say that the mass is just right. What would give you a molar mass that's too small? You said what was your molar mass?
130.
130. Okay, so what would give you a molar mass that's too small?
The amount. I don't know. A lot of things could have gone wrong in this lab.
Well, right here, the amount would be what? Too low or too high?
So let's say it's just too low.
Okay, so this is low. So instead of 1 mole, you get 0.9 moles, okay? Because for 138 grams, you should have 0.1 mole, right?
Mm-hmm.
But if your amount is too low, let's see what happens here. Are you going to get a number here that's too low or too high?
It'll be too high.
Okay, so you can't have lost material. That's not the reason. So your amount is too what?
Too
High, right?
high.
So if this were 1.1 mole, then you would get a molar mass that's too low. So why might you get a mass that's too high? And you have to think about, how did you collect your unknown? Or, how did you collect your calcium carbonate? That looks like chocolate milk she's got in her hand.
I don't know. I mean,
You filtered it, right?
yeah,
And then after you filtered it, what did you do?
I let it sit for a day, and then I put it in the oven as well.
Okay. And you dried it, right?
Yeah, maybe it wasn't dry enough
How do you know it was completely dry?
because I put it in the oven and then I put it in the oven again for another hour, and I didn't feel like it was changing that much.
Did it change at all?
I have the So it says dun, dun, dun. Mass after 1 hour in the oven was 1.60 grams. And then mass after second hour was, oh yeah. Honestly, I was having problems with the scale. It was just kind of giving me really wacky numbers. 1.68 grams. So it's like so I put in the hour in the oven for an hour at 200 degrees Fahrenheit after leaving it out for a day, 24 hours. Well, actually, probably was overnight. And then it was 1.60 grams. And then after putting in the oven for a second hour, it actually went up to 1.68 grams. I was like, that doesn't make sense at all. But I was like, I just, huh?
What you might want to do is redo your numbers with 1.60 instead of 1.68.
Oh, okay.
See if that gives you a better molar mass. Because what you are really supposed to do is heat it until it becomes a constant mass.
Yeah, it was just really strange for me. I'm like, why would it go up? But yeah, I used 1.68 for my results.
I don't know why it would go up. It doesn't seem, I can't think of a good reason.
I thought I don't know what I was doing with the scale, but it was going up instead of going down, and I was like, how does that even happen?
Yeah, sounds like a problem with the scale too, possibly. So those are the things that you talk about in your discussion.
Okay.
What are the reasons why the numbers are off? Maybe you rework the numbers with the initial mass of 1.60 and you say, wow, that worked. Okay.
Okay.
That's the kind of stuff you include in your discussion.
Okay.
The molar mass was found to be blank. And so therefore we think it's blank with this percent air. Now, how would, in the case of the calcium carbonate lab, how would you like people to see that you think it's potassium carbonate other than stating it? I mean, how would people be able to look at yours and say, oh yeah, it's calcium carbonate?
Potassium carbonate.
I'm sorry, potassium carbonate.
Because of how close the percent error would be, or just how low the percent error would be.
I would say this. Can you see what I'm writing?
It can't be closer to any of the other ones. I mean, it's just the closest one.
You got this as 138, right?
Yeah.
And what is your unknown was 130, correct?
Yeah.
Lithium carbonate is around 80.
Yeah.
And sodium carbonate is around 106. And I'm not sure what calcium carbonate is, but 60 plus whatever calcium is. So that's probably around 100. So you can just visually look and see, oh, okay, it's closest to calcium carbonate. So you could make a table and put all of this information in it. And you see how handy it is to say, oh, I can see why This person thought it was potassium carbonate.
But also my tools are only correct up to 2 sig figs, so I can't really like
Well, not
closer.
these. These are good to 3 zig figs.
No, I'm talking about my results are only good to 2 sig figs, so
Right.
can't really get any closer than that.
Yeah, you would talk about that too.
Otherwise, it'd be 140. It'd either be like 140 or it'd be 130.
Right. So that may be the major reason why you came under, because of your 2 zig figs.
It was really weird when I was doing this lab because there were multiple times where I thought like I was losing, because it kind of seemed like it was like the water was getting foggy when it was like it wasn't like part of the precipitate was going through into the water because it looked kind of murky.
Okay, yeah, and that's unlikely because the filter
Yeah.
paper I gave you was pretty dense.
Yeah, I don't know. It was strange
Well,
to me. That's why I thought I was gonna be really off with my results because I was like, it kind of seems like it's going through, but at this point, that's why I did it twice because I was like, the first time it happened and then it happened again the second time, and I was like, well, at this point, I have to just go with the numbers.
Yeah, but you did get the proper result.
Yeah, I don't know. Maybe it wasn't as murky as I thought.
So you got the proper result. And that's what usually happens with this lab. All right, so we've talked about the labs. Did you guys want to talk about the introductions at all? Okay.
No, I think I'm good. I mean, after seeing the sample one, I feel pretty comfortable.
Yeah. The hardest part for most people is going to be to write out the procedure like a story instead of bullet points, but that's what you do. And in the procedure, you'll notice that's where you include the data.
Yeah.
Usually in the procedure, when you're including the data, you don't include calculations for that data. Like if you get a mass by difference, you don't put the mass was blank by difference. You just say the mass was blah. And the idea with the procedure is that it should be enough detail for a person to repeat your lab if they've had the Chem 1A experience. So if you say, you know, like let's say there's a lab where you say the volume of water was found to be 31, or actually like the density lab. The mass of the pennies was, or the volume of the pennies was 50.1 milliliters by difference. You don't need to tell people, well, I put them in water and here's the initial volume and here's the final volume. When you say by difference, a Chem 1A student should know, oh, they're sticking that stuff in water. Does that make any sense?
Yeah. Mm-hmm.
So that's the kind of stuff you want to do with your procedures. You want to put the data in there, but tell people with words what you did.
Okay.
Okay. What can I help you all with question-wise or material-wise? Anyone have any specific problems they want me to do?
No, I don't, but I would really like to go over reactions. I have all of the reactions that you said were need to know in that video you recorded, I think, along with the homework. I just really want to drill them in and make sure I am comfortable with all of
I
them.
think I forgot 2 reactions in there, but let's look at the reactions. I'm going to give you the list, okay?
Okay.
So for alkanes, and actually cycloalkanes, you should know halogenation and combustion. So halogenation basically looks like this. Where you take a hydrogen off of a carbon and you replace it with a halogen, and your other product is an acid. Combustion could be like here's a cycloalkane. And here I'm going to put, I'm going to say unbalanced, but you should be able to balance this. Fair enough?
Question about the combustion.
Yeah.
How do we draw that with line drawings? The CO2, like where does,
Oh,
um,
CO2 with line drawings?
well, how do we do the reaction written out in line drawings?
A CO2 is never drawn with line drawings because it would look like this.
Okay.
And that's confusing, correct?
Yeah, so if we were doing a combustion reaction, obviously we know that the products are carbon dioxide and water. So it's okay to just write that as the formula.
Yeah.
Um,
Well, if you're asked to write out the reaction and it doesn't say write out the reaction with structures, then you could do this.
okay.
So what could you do? What could you do here instead of a structure? You could write C3H what?
6?
That's right.
Okay.
So the reason I drew the triangle here is so that you knew that you can do a combustion with a cycloalkane.
Okay.
Okay, alkenes. You should know addition reactions. So the addition reactions are when you take an alkene, excuse me, and you add AB.
So that could be a form of halogenation, hydrogenation,
Yeah,
or hydration.
exactly. So what I'm doing here is I'm just giving you the type of reaction. So this could be Cl2, it could be Br2, it could be F2, it could be I2, it could be H2, it could be H2O. And
So,
in this case for H2O, A could be HO and B could be H or vice versa.
right.
And then you should also know polymerization. So if we have this, and you had N of those, and I asked you for the polymer would look just like the alkene, but without the double bond. And you would have bonds coming off of those carbons in opposite directions, and that would be the polymer. I mean, that one's a piece of cake, right?
Can we talk about the example you gave in the video, the diacid and diol?
That's not an alkene. So we can do that, we will, but let's focus on the alkenes for the moment, okay?
Okay.
Combustion, you should know that if you take an alkene plus O2, you're going to get CO2 and H2O. All righty?
Yeah.
Now we're going to move on to carboxylic acid reactions. Actually, we're going to go to amines. So this isn't the reaction that I talked about in that video, but I have talked about it. Amines plus an acid give you
An amide and water.
not an amide.
Nope.
They react as follows. So let me just give you a very simple amine. So amines can act like a base. That means they can accept a proton. And we know HCl is an acid and it can give up a proton. When HCl gives up a proton, both of these bonding electrons end up on chlorine like that. And you get the chloride ion. Now, this is a free-floating proton, so to speak, right now. But what happens is the lone pair on nitrogen can bond to that proton. So this is nitrogen making a fourth bond, and it's going to have a positive sign on it for a formal charge. So amines can react like bases with acids. You should know that about amines. So it's a really easy reaction. All you do is you put a hydrogen on nitrogen and it becomes a positive charge. And then,
because ammonia NH3 is a positive.
well, ammonium is.
Okay.
Yeah, in fact, ammonium can do the same thing. I should say ammonia can do the same thing and become ammonium. So here's what happens with ammonia.
Yeah.
You get the chloride again, but ammonia becomes ammonium. And I'm saying these words really weird just to make sure that through the Zoom, it's clear that this is ammonium and this is ammonia. So this is the same reaction. Can you see that the lone pair on nitrogen forms a bond to an H plus? And I know it's an H plus because this is neutral, right? NH3. And this is a positive charge. Well, the only way this can be a positive is if we add an H plus to this. So this is the way we think of the reaction is going. So this is an H plus, and that bonds to that. So you should know that reaction. It's really straightforward. Now let's look at the carboxylic acid reactions. So the simplest one first is that carboxylic acids are acids. So this is a very simple carboxylic acid. It's called acetic acid. And that means it's a proton donor. And I'm actually going to have it react with an amine because an amine is a proton acceptor. So let's make this a CH3 on the bottom here. So what do we know is going to happen to the amine?
It's going to bond with that hydrogen.
Right. And what happens to the sign on the nitrogen?
Becomes positive.
Right. And then if we're taking this hydrogen right there, these electrons end up right here. And when I redraw the carboxylic acid, I want you to notice that that oxygen still has an octet because both electrons from the bond ended up on oxygen. Now, what is the charge on an oxygen that has 6 electrons that are not bonding and 2 electrons that are bonding? And the answer is -1. So we have 2 neutral molecules becoming a cation and an anion, and together, collectively, these are neutral when you add the charges together. So it's not hard to remember that carboxylic acids are acids, right? Because the name says so.
Yeah.
Now, the carboxylic acid reaction you also want to know is that a carboxylic acid plus an alcohol can become an ester plus water.
Yeah.
Or vice versa. And a carboxylic acid plus an amine can become an amide plus water, or vice versa. So let's look at each one of these in turn. Let's look at the carboxylic acid plus an alcohol makes an ester plus water. So here I'm going to just draw carboxylic acid, a simple one. There's my carboxylic acid. And then for my alcohol, I'm going to draw this. And I'm drawing them this way on purpose to kind of confuse you. Because on the test, you never know what's going to happen. But in these reactions, when you take the carboxylic acid and the alcohol to form ester and water, the water is always formed from that OH on the carboxylic acid. And
Right.
that hydrogen from the alcohol.
Mhm.
So I'm going to put H2O from these two. Now we take these two pieces and put them together. To me, the easiest thing, is to take the carboxylic acid and take this alcohol, and I'm going to turn it around. Do you see how these two alcohols are the same? I've just turned it around, flipped it over, whatever you want to call it. So I'm going to add this piece to this piece here. And there's your ester.
Yeah.
So that's the carboxylic acid and alcohol. Now, what happens if you have something like this? So this is called a diacid. Can you see how it has an acid on the left and the right?
Yeah.
And we're going to add it to this guy here. And this is a dialcohol.
Yeah.
So here, this and this combine together to make what?
Water.
Yes. But this combines with a hydrogen from another alcohol and makes what?
Water.
Yes. And this hydrogen combines with another acid to make what?
So this is a polymerization reaction.
Right, because both ends react. So imagine if you are a diacid. So your left hand can bind to an alcohol and your right hand can bind to an alcohol. You with me?
Sure.
And it would be better if your husband were around because you could hold his hand. And then now you've made a bond to your husband, who's the diol, and he could take his other hand and make a bond to your niece, who's a diacid like you, right? And then your niece could bond to another diol, and it can go on and on forever. And you make this great big long string of molecules that are bonded together. So how do you draw the answer? And the answer is, do you see this diacid and these OHs that we're taking away to make water?
Yeah.
You draw the diacid without those OHs. And I'm going to go ahead and do this because that's the OH is gone. You with me?
Yeah. So we have CH3s at the end.
No, we're not done yet. Now
Oh,
this connects to that oxygen.
yeah.
Okay. And I'm going to cross this guy off and we do that. So here, this is the alcohol without its hydrogens. This is the acid without its OHs. So basically I'm taking this and combining it with this. So let's see that again. I'm taking this and I'm combining it with this. Now, what do? I put this here, and that's the polymer. There are other ways of doing this. Like if we didn't have line drawings, let me show you how it would go, okay?
Okay.
So if we didn't have line drawings, but we had this instead, and we want to know what the polymer is, what we would do is we would take this piece. Do you see that's the acid without the two OHs?
Mm-hmm.
And here we would take this piece. Do you see how this is the alcohol without the H's?
Yeah.
And we just bond those together. Boom, boom. And there's the polymer. What else do we make?
Water.
No, it's water. So that's the polymerization reaction. And this is called a polyester because that's an ester bond. That's going to be an ester bond. That's going to be an ester bond. And it's just ester after ester. So you might have better luck. You might like this, using the structures like this better than the line drawings. And if that's the case, and you're given line drawings, what do you need to do?
Turn it into that.
Turn them into that. Okay. Tools of the trade are make the problem easy for you to do. That's what you're supposed to do. Fair enough? Now, let's look at the carboxylic acid plus an amine. And this makes an amide plus water. So here I'm going to go ahead and start with a very simple carboxylic acid. And here's my amine. I'm going to make this easy on us. So this amine has to have a hydrogen. And it has to have a hydrogen because...
Question about amine real quick.
Yeah.
So an amine doesn't have to be NH2?
No, it can be NH1. It can be NN. These are all amines.
Okay.
Let me show you. We'll put an isopropyl group on it, okay? That's an amine. That's an amine. That's an amine. So how many hydrogens are attached to this nitrogen? 2. How many hydrogens are attached to this one? 1. How many hydrogens are attached to this one? None. The focus of an amine is that it has to have a carbon bonded to a nitrogen. And that is right here. And for this one, you could say it's right here or it's right here, your choice. And here you could say it's right here or right here or right here. In fact, this is called a triamine. And this is called a diamine. Because really there's 2 amines here. Are you with me there or not?
Yeah, I mean, I guess if you're sharing the nitrogen.
Yeah.
Okay.
So we don't worry. I'm not going to worry about this. Like on the test, if I show you an amine, you don't need to tell me if it's a diamine or a triamine. Just, it's an amine.
Okay.
So as long as we see that bond, it's an amine.
Yeah. But if you see this, that looks like an amine, right? But if we do that, it's an amide. So
Right.
this has a carbon-nitrogen bond, but the carbon also has a double bonded oxygen, which makes it really special. Now, what about this? What do we have here?
I say it's an amine,
That's an
And-
amine
a ketone.
and a ketone. That's correct.
Okay.
So why did I show you this example?
To get tricky.
Not to get tricky, but to point out to you that the carbon bonded to the nitrogen has to have the double bonded oxygen to be an amide. If it's not right on that next carbon, that oxygen, it's not an amide.
Yeah.
Okay. So not to be tricky, but to show you the fine detail.
And the ketone is just differentiated by the extra carbon.
Yeah, a ketone has to have 3 carbons in a row, plus whatever. It could be 10 carbons in a row. But for the 3 carbons that you're looking at, the middle one has to have a double bonded oxygen. That's a ketone.
Okay.
So this is a ketone. You see the 3 carbons in a row with the double bonded oxygen on the middle?
Right.
This is a ketone. You see the 3 carbons in a row with an oxygen in the middle?
Mm-hmm.
This is a ketone.
Yeah. As long as you have that there, then you can, that part is a ketone.
Yep. Now what happens if I do this? Is that still a ketone?
Yeah.
Yes, it is, because it's still got the 3 carbons and the double bonded oxygen. What's this guy down here? A COH.
Alcohol.
Alcohol.
Okay.
That's right. Okay, so back to carboxylic acids and amines. What happens here, and I'm going to do this now. What do those things make?
Busy.
What's that?
Water.
Yes. Or what does it make, Charlotte?
A water.
Okay. No, I thought it was water.
No, I'm done.
Okay, so I'm going to take this piece here that's left over and attach it to this piece, and boom, you've got your product. And what is this guy called when we have a carbon bonded to a nitrogen, but the carbon has a double bonded oxygen?
Amide.
Amide. And of course, the reverse can happen.
Yeah.
Now, what happens if you have this? So that's my diacid. And that's my diol. So how did we draw the polymer using the acid? And, oh, my bad, we don't want a diol. We've already done this type of reaction. We want a diamine. So I'm going to do this. So what part do we keep of the acid? We keep that part.
We keep the OH. Yeah, the OHs is what is going to fall off.
And become
Water.
water.
Become water. Sounds like Bruce Lee.
Right. Or it sounds like a mother talking to her child. Do you need to make water? A very young child.
Yeah.
Very quickly they learn it's pee. Okay, so I'm going to take this hydrogen off, right? But notice the one going down is still there. Are you with me or not?
Mm-hmm.
So I'm taking these off and this off and that
Yeah.
off. And then what do we do once we take those off on the ends? We put parentheses through the bond. And so what does this mean? This means the following. You probably don't want to write this because it is laborious. Okay, there's one of them, right?
Mhm.
Now, what am I going to attach here?
Carbon. Double bond.
Yeah. A second amide.
Yep.
So an amide can be like
And what am I?
small or big. Another one.
Another one. So it just keeps going. And here you can see this is an amide bond. This is an amide bond, but it's kind of backwards, right? Because the carbon goes to the nitrogen to the left instead of to the right. But it's still an amide. And this is going to be an amide bond. And this, I guess I might as well just go to the end. Oop, thank goodness I finally ran out. This is an amide bond. This is an amide bond. And it goes on until you run out of units. So don't you think this is a much nicer way to write this?
Yeah.
Why are you pointing the arrow between every carbon and nitrogen?
Well, because it's an amide bond,
Okay.
right? Because here, isn't that an amide, carbon bonded to nitrogen, but you got the double bond.
Oh, because that's the oh, got it.
So here's another
That's
amide.
the part of the bond. That's the amide. Yeah.
Yeah. So if you're looking for functional groups, those are amides. What are these guys?
Aromatic.
Aromatic.
And that's all the functional groups we have here, huh?
That's it. You only have amides and aromatics in this guy.
Yeah. I guess like my confusion is like all of that together is still considered an amide, even though there's aromatic in there. I don't know.
Well, it's really a polyamide
Oh, no.
and a polyaromatic, right?
Mhm. But like for example, in okay, but we don't say like okay, a carbolic acid and amine yields a polyaromatic and polyamides. It's
A,
water.
a carboxylic acid and an amine yield an amide. And that's still happening here. Isn't this a carboxylic acid that I'm pointing at?
Yeah.
Isn't this an amine that I'm pointing at?
Yeah.
And when they combine together, doesn't it make an amide?
Yeah, but also you also have the aromatic. So like what does that do? Or do you have to mention it?
It's not reacting, is it?
Oh, okay. Is that why it's not okay, part of the
So what I'm saying
yield?
is in this reaction, this piece of the molecule reacts and this piece reacts,
Exactly.
but the
Mhm.
aromatic doesn't.
Right. So they're just spectators.
They're just connecting pieces.
Okay.
That's all. They're just
Yeah.
connecting pieces.
So they're just kind of hanging along, but not.
Well, they're holding together the two acids, right? Or the two
Yeah.
amides. So you need a piece to hold together the two pieces so that you can make a chain.
Okay. They're not necessary. It's just kind of.
Well, no, they're not necessary, but if you put different things there, it'll give you different characteristics to the polyamide.
Right. Okay.
And so that's why you use different pieces in there. Now, let's take a look at this guy down here. Do you see that the repeating unit can be thought of as being here? Let's see. I'm going to start right here, and I'm going to end right here, and start again here, and end here. Do you see how this is exactly the same as that?
Mhm.
So I'm going to draw this again. So we want to make the polymer from this acid, this diacid, and this diamine. And there are two correct answers. So here's one of the answers. So what am I starting with here? The diacid or the diamine?
Acid.
Diacid. And of course I take the OHs off. And on the diamine, I take one H off each side. So here's one answer. Are you ready for the next answer?
Mhm.
The next answer is this. So here I'm starting with the diamine, not the diacid. So this is the other correct way to write the answer. These are the same answer.
So would this be considered a base?
A what?
Would it be considered a base, this product?
This?
Yeah,
Amides aren't really bases. They're not good bases.
okay.
Certain amides are good bases, certain ones aren't. This one is not. So you're referring to the amine reaction, right?
Yeah.
Yeah, and that's, you want to focus on that's being good for amines, not for amides.
Okay.
And the reason is that for the amine reaction, you have to have that lone pair being available to make a bond, right?
Mm-hmm.
The reason amides are not, so we have a lone pair on the amide, right? The reason this lone pair is not that available is because the lone pair is actually kind of resonating with electrons on the carbon and the oxygen. So those electrons are not available to go out and bond to a hydrogen because they're kind of hanging out with their buddies, the carbonyl. So it's a great question. Do amides react like bases? And the answer is not really. Okay. And we can see that with the resonance structure. See, this is clearly not going to bond to an H plus, correct?
Yeah.
So if this is a resonance structure and it's got a plus sign, and here you've got no plus sign, that means that nitrogen has a slightly positive character, which means, guess what? It's not going to like an H plus.
Yeah.
It's not even going to wink at it. Okay. All right. So those are pretty much the sum of the reactions that I would like you to know, Charlotte. So if we do a quick review for alkanes, you should know halogenation. Now for the halogenation of alkanes, what's the one thing that I didn't write down that you also need? Light.
Light.
Okay, and there's combustion. For the, and this is for cycloalkanes too. For alkenes, you've got the addition reactions, and you've got the polymerization, and you got combustion. Now I'm going to tell you that this one and this one also works for alkynes.
We haven't talked a lot about alkynes.
Well, it's the exact same reaction because alkynes, for an alkene, you got a sigma and a pi bond, right?
Yeah.
And for an alkyne, you've got a sigma and 2 pi's, right?
Yeah.
Well, in the addition reaction, one of the pi's is reacting. So alkynes can polymerize. But remember how when we redrew this guy, so I'm going to put AB here.
Yeah.
AB. So you would get this for your polymer. Only one of the pi bonds goes away.
Okay.
Whereas this guy would do this. Right? The pi bond goes away.
Right.
Here, one of the pi bonds would go away. So you can do that. You can polymerize alkynes, and they can also combust. And for addition reactions for an alkyne, you could do this. And you could do it again because it's an alkene with it that could react. Are you with me there?
Yeah, then we have an alkane.
So that's why we don't talk about alkyne reactions. They're going to do just the same as alkenes, but twice as much in most cases, right?
Yeah, I guess so.
Okay, and then there's the amines. Amines are what? They're a base that can add a hydrogen. Carboxylic acids are an acid that can lose a hydrogen. And carboxylic acid and amines can make amides. Carboxylic acid plus an alcohol can make an ester. And then a diacid plus a diamine can make a polyamide. And then a diacid plus a diol can make a polyester. And really, when you think about it, there's only one type of reaction here. And the type of reaction is that this X could be nitrogen or oxygen, right?
Yeah.
Okay, so what's going to happen here? Those go away and become water. And you bond to that X, which is either a nitrogen or an oxygen, and all of the extra stuff that comes with it. So that's it. Now, you should also know the backwards, right?
Hydrolysis.
Yeah, like if I give you this, you solve the problem in your homework. So this is the bond that gets formed when you make an ester. It's also the bond that breaks. So here's the bond broken. So I'm going to put the little stubs here of the leftover bond. But here, you add OH here, and you add H here. And do you remember you sent me that your assignment and you kind of connected these guys?
Yeah,
You don't want to do that.
I see now.
I mean, it was a good try, but that's why I give that assignment, is so that you understand that you are breaking the bond between those two atoms, this carbon and that oxygen. They're no longer holding hands. Okay?
Yeah.
So let me ask you this. Suppose you have this. What bond are you going to break?
Nitrogen carbon single bond.
Okay. What are you going to add to the double bonded oxygen carbon?
OH.
And what are you going to add to this nitrogen?
H.
And there's a space there between those, right?
Yeah.
So if you wanted to, you could even draw this like this and it would be correct. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. And then NH2. This is the answer. They're the same thing. Which one is probably a better answer, though? Don't you think the top one is, because you can see where it came apart?
Yeah.
Here, you got to take this guy and fold it all up in your mind, and good luck. Can you see how this could be turned into that by making the amide? It's kind of hard to tell, right?
Yeah.
But can you see how this guy can be turned into that by taking away the OH and the H?
Yep.
So then what do? We just put a line between oxygen and nitrogen, or carbon and nitrogen, like that, and boom, you got your answer. Oh, we lost Issa.
Oh,
I
got
didn't even
tired
hear.
of it.
She got tired of all this crap.
A whole the reaction.
It was probably 11 o'clock and she had to leave.
Okay.
When people have jobs,
Oh.
appointments,
Okay, how do I practice these reactions?
do as many problems in the back of the book as you can that deal with these types of reactions. There are some
Look, I did.
questions in the back that ask you to do polymerization.
Okay.
As far as, let's see. And then if you want, you can always go to another website and say, polymerization reactions with carboxylic acids. Okay, 1110-ish around there, right?
Yeah.
Okay, so there's a whole section here on polymers. It's got 1, 2, 3, 4 problems. And then when you go to the general questions, let's see. 83 is a polymer reaction. 84 is kind of like a polymer reaction because it's the reverse of it. You're hydrolyzing it.
Yeah, I did it.
Did you understand what you were doing at the time?
I don't know. I should do it again.
Yes, you should. Here's another one, 96.
Oh, I did it right.
But when you did it, did you do it with confidence?
Probably not.
So maybe by redoing it and not looking at your notes, you might be able to do it with confidence.
Yeah.
What about 102? Did you do that one?
No.
How about 106? That's a hydrolysis. It's not really polymerization, but it is hydrolysis. 106.
Okay.
Let's see.
Um,
120 isn't really making a polymer. It's more about studying them. That's it. But that's quite a few problems.
okay.
Plus, you can go back to the polymer section in the chapter and do the in-chapter problems too.
Okay.
That's what I would suggest. But I would first start with the ones that you've already done. It's probably enough time has lapsed.
Yeah.
Like Issa's getting back in.
Yeah.
All right, Issa, where'd you go? Can you hear me, Issa? Can you hear me, Issa?
So for 71, it asks about vinyl.
Stopped. Sorry.
Oh,
We were just talking about more about polymer reactions. I'm sorry.
are we supposed to we're supposed to look up what vinyl acetate is?
Yep. And
Okay.
if you look up vinyl acetate, so number 71, it's got to be near page 1110. You said it was 71?
Problem 71.
Okay, polyvinyl acetate is the binder in water balanced paints. Write an equation for its formula from vinyl acetate. So you know this is a polymer reaction. I would go to the polymer section
Okay.
and see if I could find vinyl acetate. So if we look on page 1098, can you see it tells us what vinyl acetate is?
Yeah. Okay.
So once you see that, it becomes straightforward. When you draw the polymer, we've just learned that the best way to do it is this way. So this is vinyl acetate, and we're going to do O. Oop. That should not be an O, it should be a carbon. So carbon, double bond O, OCH3. And we have N of these, and when this makes the polymer, we draw the same darn thing without the double bond. Exactly the same way.
Is it with water?
No,
Just
there's no leftovers here.
So how are we going from the reactants to the products? What is making it react?
An initiator.
And that's just implied.
Yep. Well, it's a detail that I can tell you about if you want to see it, but it could be confusing.
No, I'm okay.
Okay.
So
there's your polymer.
but the hydrogens, we're not removing any hydrogen.
Okay, it's clear to me that you want to know what's going on because it's confusing you not knowing. Is that right?
Yeah, I guess so. Yeah.
Okay, so I'm going to redraw this guy, but I'm going to actually take this away.
Because
and I'm going to draw a carbon-carbon double bond with hydrogens on it like this, okay?
Uh-huh.
Okay, now do you see the other carbon-carbon double bond? I'm drawing 2 dots there instead of a line, okay?
Okay.
And then I'm going to draw another one of these, just like that, with 2 dots. And another one. So these are the alkenes that we're going to add together. So there's something called an initiator. And the initiator has a single electron. And what the single electron does is it makes a bond to this carbon right here. But you can't have a 1 electron bond. So what happens is one of these electrons comes and it makes a bond. So the initiator makes a bond to this carbon here. And this bond is formed from 1 electron from the double bond and 1 electron from the initiator.
So
Now this guy here
one goes over there.
is an initiator. So it's going to form a bond to this carbon but you need 2 electrons to make a bond. So what's going to happen is one of these electrons is going to combine with that guy to make a bond. And you're going to have 1 electron left over. Guess what that electron is going to do?
So Tony, for this polymerization reaction, like the examples we were just working on, we were taking away hydrogens and oxygen.
We are not taking away hydrogens in this reaction.
So in this one, we're not doing that.
That's why they're called addition reactions.
And the other ones was a condensation polymerization.
Yep. Where one of the products is water, which means you're taking away H2O essentially. But this one, there's nothing left over, right?
No, I guess not.
Now, how long does this go on?
Well,
Thousands of molecules long. So when you have thousands of molecules long, doesn't this represent what you have? Even though you have initiator at this end and you have some sort of terminator at this end, when you have thousands of these and only one of these and one of these, for all practical purposes, these things don't exist. Are you with me here or not?
Yeah.
So that's why we don't write the initiator in or the terminator in. We just write down what's in the middle because there's thousands and thousands of them.
It's just a chain reaction.
Yep. It's just a chain reaction. So, you know, if you imagine you have 1,000 people lined up next to one another and something initiates a reaction where you hold hands with the first person, and they hold hands with the next person, and so forth and so on. It just goes on forever until there's something at the end which holds the last person's hand and you're done. And what happens in that reaction of holding hands? Does anything get lost? And the answer is no. And does anything get added? No. But do you change the way things are bonded together? Yes. And here we have all these pi bonds in these individual pieces, correct? But in the polymer, you don't have any pi bonds, so we're changing how they're being held together. So if you think about it, what is the geometry of these guys? They're all sp2, right? Which is trigonoplanar, right?
Yeah.
And what's the geometries in all of these? sp3, which means they're tetrahedral.
Yeah.
So that's kind of interesting that when these all react, they change from trigonoplanar to tetrahedral. So pretty cool stuff here. All right. Oh, so we're supposed to go back to 71. Let's finish it since you asked about that one. So there's the answer to A. Show a portion of this monomer with three units. So here's 1 unit. And because I'm really lazy, you see this thing right here? I'm going to say that's A. So that's 3 monomer units. This would be unit 1, unit 2, and unit 3. Are you with me there? And C says, show a portion of this polymer. Oh, describe how to make polyvinyl alcohol from polyvinyl acetate. So how can we make polyvinyl alcohol from this?
You need an OH. Could we add water?
Actually, polyvinyl alcohol. Let me think about this. Uh, this is a hard question. It's not easy at all. So we're not going to do it.
But couldn't we?
I think that means, Charlotte, that we don't have to worry about it.
I know.
So what you would do is you would reduce this.
So
So don't worry about it.
I draw. Okay.
You don't need to worry about it.
Okay.
See, don't worry about it. Or forget about, how do you say it? How do you spell about it? Forget about it. Forget about it.
At least until you have to learn about it in the future.
Learn how to do it in organic chemistry where you have a year to learn these things. Okay.
Charlotte doesn't seem convinced. She's like,
Okay.
Don't worry, Charlotte. When you take organic chemistry, they will answer all these questions. And if they don't, your teacher sucks.
Oh.
But they will have time to answer these questions. We don't really have time to go into that kind of stuff.
yeah, this is just an introduction to organic chemistry.
Yeah. And the fact that you show an interest in it is good because if you want to reach your goals, you're going to have to take a year of organic.
Mhm.
What are you trying to do, Charlotte?
Medical school.
Oh, cool.
Mhm.
You have lots of this to look forward to.
Yeah. Yeah. Biochem.
Nice. Good for you.
Yeah. Good for me.
You know what's going to happen though, Issa? She's going
Uh-huh.
to take all these chemistry classes and she's going to say, you know what? I'm going to become a chemist. I'm not going to waste all this time I've spent learning chemistry and just become a doctor.
Fair.
Doctors, what do? They save lives one by one, or they make your quality of life better, right? One by one.
We need doctors. I wish people didn't have to pay to go to med school. That's the worst. I mean, what a bad incentive. Like it's already hard enough to go through med school, and then you have to like worry about like how expensive it is. Like that's not cool.
There is not a single med school student that worries about how much med school costs because they know
they're gonna get compensated. Yeah, that's true.
They know that when they're a resident, they're basically going to be able to pay off their med school costs.
That's true.
I mean, have you ever seen a doctor who was, say, 35 years old who was worried about the mortgage?
Yeah, but I also feel like we need doctors in like spaces that aren't where they may not necessarily make a lot of money as well. So like out here, for example, in like Humboldt County, a lot of doctors don't want to come here because there's not a lot of incentives, you know?
Well, they have programs for that.
They have loan forgiveness programs for
Yeah.
docs who want to come to rural areas for that reason.
That's good.
The doctor who helped with the birth of my son, he was one of those doctors.
Yeah, you need that.
And he worked at the Indian Health Clinic and Indian Healthcare Clinic, and it was great. He was a really accomplished doctor, knew what he was doing, and liked what he was doing. And he was doing that kind of loan forgiveness thing.
Yeah.
Did you know that's where I work, Tony?
Pardon me?
Did you know that's where I work?
In Crescent City or in Eureka?
In Crescent City.
Okay, no, I didn't know that.
Yeah, Indian Health.
So my wife is Native American. I'm not. My kids are too, of course.
Well, yeah, that's how that works.
I'm the odd person out in that particular situation.
Yeah, so am I. My husband's Native, but I'm not. So I was able to go to that clinic. Wow.
Oh, so we're kind of alike.
Yeah.
Oh, it's
We're
interesting.
the outsider.
Yeah, and now I work there as an outsider, and they of course give, with good reason, preference to Native employees, but I'm not. So
Right, but they'll also hire people if they don't have enough of pool of the Native employees.
Which hospital is this? I'm sorry.
Oh, it's not. It's United Indian Health Services, not a hospital,
Oh, okay, okay.
clinic.
Now, the one my family goes to is the one in Arcata.
Got a lot.
Yep.
And they only accept people of native descent, or it's for everyone?
It's mostly for people of Native descent or related
Oh.
to them.
Oh, okay, okay.
Yeah.
Yeah.
But I think that, if they have an emergency room, they wouldn't turn away someone.
Hmm.
And I think you may be able to use them if you pay for their services. But if you're basically of Native descent, you're on a tribal roll, it's essentially free.
Mm.
Yeah. If you're not Native, you need health insurance.
Yes. So, you can go there, but you'll need health insurance if you're not Native.
Do you know, Charlotte, what's the best health insurance plan to have up here?
Health
Anything,
insurance? No, no idea.
anything is better than nothing.
Right.
It's true. Yeah. No, I don't know.
The best health insurance is to eat right and don't do stupid things
Yeah, if only people thought of it that way.
and exercise daily.
Yep.
Like me, I
True.
went out for my 2-mile walk and 10-mile ride.
Yeah. Yeah.
Tony, I'm gonna do these polymerization problems and then bug you at 1:15.
That's fine. I will be here.
Are you gonna show up?
Yeah, I do show up.
You're not gonna be tired of it by that time?
I do show up unless you don't call in by 1:30, then I just shut it down.
Okay,
So
Yeah.
if you don't show up by 1:30, I'm going to shut it down.
okay.
So I won't be what is it, logging in at 6 today, but I will show up tomorrow.
Okay, well, Rebecca often shows up around 6, so
Okay, cool.
I'll be there at 6.
All right. Well, thank you so much, Tony.
You're welcome.
All right. Have a good one, Charlotte.
All right, Charlotte,
Bye.
we'll see you later this afternoon.
And bye.
Bye-bye.